Hello everyone, my name is Mark Leuis from BSED Science 3A, and in this video I am going to discuss my solutions with regards to the two problems in time dilation. So here is my problem number 1. So an astronaut in the near future flies on a rocket and travels to Proxima Centauri and back and returns home in 12 years. The rocket travels at a speed of 80% of the speed of light. Upon return, how much they have aged by. So first, we are going to identify our given, which are, so for our velocity, we have 0.8 the speed of light, and we have here our dilated time, or the time measured outside of the reference frame, which is equal to 12 years, and we are going to look for the t-naught, or the proper time. So the formula that we are going to use is the formula for time dilation, which is the delta t, or the dilated time, is equal to the delta t-naught, or the proper time, divided by the square root of 1 minus v squared over c squared. So if we are going to substitute all the given to the equation, and we have 12 years is equal to the delta t-naught divided by the square root of 1 minus 0.8 the speed of light squared over c squared. So we can cancel out the c squared. And so we have 12 years is equal to the delta t-naught divided by the square root of 1 minus 0.64. We have 0.64 because we squared the 0.8. And so we are going to cross multiply and to get the value of the t-naught. So we have here our delta t-naught is equal to 12 years times 0.6. So we have 0.6 because it is the square root of 1 minus 0.64. So if we are going to multiply the 12 years times 0.6, and we have the value for our t-naught is equal to 7.2 years. So this means that the astronaut has aged 7.2 years relative to our aging, which is 12 years. So that's all for our problem number 1. So now let's move on to the problem number 2. So we have here the star Sirius, the brightest in the night sky, is 8.6 light years from Earth. If you traveled in a ship at 0.75 the speed of light, an observer on Earth calculates that it will take you 15 years to get there. How long would you measure it to take? So first, we are going to identify our given, which are our delta t, or the dilated time, is equal to 15 years. So this is the calculation of the observer on Earth. And we are going to find for our delta t-naught, or our proper time. And our velocity is equal to 0.75 the speed of light. So to find for the value of our delta t-naught, we are going to use the formula for time dilation, which is delta t is equal to delta t-naught divided by the square root of 1 minus v squared divided by c squared. So if we are going to substitute all the given to the equation, and we have 15 years is equal to the delta t-naught divided by the square root of 1 minus 0.75 c squared over c squared. So we have here 15 years is equal to the delta t-naught divided by the square root of 1 minus 0.5625. So we have this 0.5625 because we squared this 0.75. So we are going to cross multiply, and we have that delta T naught is equal to 15 years times 0.66. So we have 0.66 because it is the square root of 1 minus 0.5625. And if we are going to multiply 15 years times 0.66, it will be the value for our delta T naught, or the proper time, which is equal to 9.9 years. So as a person inside the reference frame, it will take you 9.9 years to get to the star Sirius compared to the calculation of the observer on Earth, which is 15 years. So that's all for the problem, for my problems in the time dilation.